Okay, thank you very much, and thanks, Gary, for setting me up here. I'm going to talk about an application of the state of the science in terms of sea level rise and storms. Look at the vulnerability of the California coast, and this is a modeling system we developed at the USGS, Coastal Storm Modeling System we call Cosmos. But I think it's a really good example of a collaboration and partnership with all different levels of government, including NGOs as well. But down to the municipal level, the state level, a lot of support from the State Coastal Conservancy, interaction with the Coastal Commission, the Ocean Protection Council. At the federal level, a lot of support internally from USGS, but also from NOAA and the National Park Service. In the background here is a look at the San Francisco airport, really probably ground zero for climate change impacts in the state, especially in terms of economic impacts. These are just some very simple sort of middle-of-the-road scenarios of flooding for the San Francisco airport over the next century. We'll get into that some more. So what is the problem? I think Gary already set this up nicely. It's a global problem, it's a regional problem, it's a local problem. Globally, from just coastal flooding alone due to sea level rise, exclusive of storms, could displace 200 million people by 2100. Nationally, about $1.5 trillion of property is at risk at high tide. But then you have an event like Hurricane Sandy, $50 billion in damage. What does that look like with a meter of sea level rise? In California, based on the work by the Pacific Institute, about 500,000 people, 1 million jobs, and 100 billion property are threatened by climate change over the next century. But then we have these extreme short-term events like El Niños. 82, 83 cost $200 million in damage to the California coast. So what do those socioeconomic numbers look like with a meter of sea level rise and an El Nino? So the kinds of things we can expect over the next century, and research by Scripps and USGS suggests actually storms aren't going to change that much. So this is the combination of storms and sea level rise. So accelerated beach erosion rates, greater incidence of cliff failures, landward translation of flooding, more dangerous navigation conditions, beach and shore safety more often compromised. And something I'm not going to talk about today, but a critical issue in this state and also globally is saltwater intrusion into coastal aquifers. Probably the #1 international security issue that is just beginning to scratch the surface on. So looking up and down the state of California, it's obvious we're vulnerable. We have a lot of low-lying areas, a lot of valuable infrastructure, a lot of people in the line of fire, so to speak. Not only private infrastructure, but public infrastructure as well. San Onofre nuclear power plant now being decommissioned, basically the deck is right at sea level. So there's a couple different approaches to try and determine coastal vulnerability. There's a static approach. This is one end member, and an excellent tool here is the NOAA Sea Level Rise Viewer. This is available nationally. So this is really an excellent first-order screening tool. If you want to look at the average, at the daily impacts of sea level rise, this is a great tool. It doesn't include storms, but has a very good tide model, has socioeconomic impacts on the migration model, good elevation control. So if you're within the footprint of these flood extent maps, then you're in big trouble. This is going to happen every single day in the future, given a certain amount of sea level rise. The other end of the spectrum is the dynamic approach, which is the one that we have taken. It's also been done by other groups for the ART project and for FEMA as well, primarily by AECOM, and also through the Nature Conservancy's Coastal Resilience tool by ESA PWA, which also supported the Pacific Institute work. This is the approach that takes storms into consideration, all the other contributions to total water levels that ultimately lead to flooding in these short-term cases. So with the Cosmos case, we use global climate models. We scale from global forcing conditions down to local flooding. We try and include all the relevant physical processes that contribute to flooding. That's wind, waves, also shoreline change. The shoreline is dynamic. It evolves through time. It's not static. Rivers, how do rivers interact along the coast? With the ocean itself, and also vertical land movement. And we try and incorporate a range of sea level rise and storm scenarios to basically match almost any planning horizon that you have, and explicitly model the flooding, and also make sure that the ocean is connected to the land hydrologically connected, so we're not just indiscriminately flooding everything below a certain elevation. It has to be connected. So why do we care about this dynamic approach? Well, the static approach will get you part of the way there, and like I said, this is a really good first-order screening approach to look at what's going to be impacted on a daily basis. But in California, by 2100, we might get about a meter of sea level rise. The tide varies by about 2 meters, or about 6.5 feet or so. But during a El Nino winter, for example, we can raise water levels by about 30 centimeters, about a foot. During extreme storm, we can, due to onshore winds and low atmospheric pressure, we can increase water levels by about a meter, about 3 feet. This is storm surge. It's not nearly as extreme as you get in the Gulf Coast. Hurricane Sandy had about 8.5 meters of storm surge. Nevertheless, it can be a tipping point. But the dominant dynamic water level increase is due to waves, and that is wave setup and wave run-up. So if you look at just those first two levels, sea level rise and tides, that accounts for about 3 meters of potential water level increase in the future. During extreme events, maybe 4 to 5 meters or even more. So we're talking 12 to 16 feet of additional water level increase that needs to be captured. So on the lower panel is just an example from Stinson Beach, 50 centimeters of sea level rise, no storm. There's a little bit of flooding, but maybe can be manageable. But then if you add that with the annual storm on the lower right, you see the entire base of that spit is completely inundated, and you have a big problem. So we've taken this approach on the lower right to try and really capture the full impact of sea level rise and storms in the future. So this is kind of what motivated the development of Cosmos, physics-based modeling system, designed primarily for California, but applications other places. We've tried to, again, predict coastal hazards for the full range of sea level rise scenarios, 0 to 2 meters, even a 5-meter extreme scenario, and all the different storms. So if you're interested in the impacts of a storm tomorrow, this winter, or the same type of storm in 100 years or more, we have a scenario to meet your needs. And importantly, we've been trying to develop the tools and the approaches with federal, state, city governments, so it directly meets their planning and adaptation needs. And this emphasis has really been on directly supporting federal and state-supported climate change guidance, for example, that the Coastal Commission has now come out with, and also the various vulnerability assessments through the various grant rounds for LCP updates and the OPC and state coastal conservancy grants as well. This is very broadly how Cosmos works. We take global climate models, we develop a future wave climate. From that, that drives regional wave models in the middle because we actually care in California about what happens in the Southern Ocean, what happens in the Western Pacific, and in the entire basin. So it's important that we understand the entire wave climate, not just what's happening immediately offshore from locally generated winds. And then we continue to downscale to the very local level so we can scale down to local hazard projections. So we start with winds on the order of 200-kilometer force in the upper left. We get down to flooding projections down to about 2 meters on the ground or about 6 or 7 foot footprint. A couple key components of any model, and Cosmos is no exception. We need very good digital elevation data. This is an oblique view of the Tijuana estuary. Imperial Beach, sort of in the middle left, and then the city of San Diego and San Diego Bay in the upper part of the screen. So we need to have very good information, elevation data on the shelf so we can propagate the waves properly, we can propagate surge properly. But then once we have flooding on the coast, we need to very clearly delineate the channel structure, the various undulations in the topography so we get the flooding right. 2-meter scale resolution. But the hydrodynamics can't be modeled quite at that scale. Nevertheless, we need to really have refined numerical grids so we can delineate these very fine-scale features in these channels and throughout the topography so we can get it right in the end. This is critical in increasing the resolution in areas that are particularly subject to impacts so we get that right as well. I mentioned the scenarios. We have about 40 to 50 scenarios in all these different areas we've been applying Cosmos to basically meet any possible planning horizon need, be it just daily sea level rise impacts or a 100-year storm and out to 2100 or beyond. The other critical component of any any such application is a web tool, so that data can be easily accessed, it can be manipulated. For more sophisticated users, you can bring in your own GIS shapefiles, you can export GIS, and this is done under the Our Coast, Our Future collaboration. There's a link at the bottom if you want to play with this. It's currently available for the San Francisco Bay Area, the Bay itself, the Outer Coast. It's coming soon to all of Southern California. In subsequent years, the rest of the state is the plan at the moment. But the number one product, people want to know what's going to get wet. So what's the extent of flooding and how deep is it going to be? And make sure that there's hydrological connectivity in the flooding. And also you can see that arrow, what areas are vulnerable but not connected to the ocean or the bay. So for example, there's a huge levee system in San Francisco Bay. And those green areas are showing areas that are below the flood elevation but not connected. If there's a levee failure, those would be wet as well. Flood duration, especially a lot of interest on the ecosystem side about how long these areas will be inundated during a particular event, how long they'll be flooded. This is another product that we've been rolling out, and based on feedback we've been getting from stakeholders. Waves, for navigation, for penetration into harbors. You can see this is an extreme event. We had about 30 to 40 foot waves on the outer coast, but you can actually generate waves inside San Francisco Bay as large as about 12 feet. That's another product that's out there. And then tidal currents, if you're interested in scour, sediment transport, there's also some information there as well. So just a quick summary of where this has been applied. Initially was in Southern California as a pilot. This was focused on the outer coast. It just took a few simple scenarios and added a historical storm, the last big El Nino storm we had in January 2010, and added some simple sea level rise scenarios to that. And this was a pretty effective way, although there weren't very many scenarios, of just identifying critical thresholds to worry about. And here's an example from Del Mar. Modeling the January 2010 storm, and that very same storm in 2050 shows there's already significant potential impacts to this region. And then if you go out to about 2100, extend it even more. And this type of product is available for the entire Southern California region right now. We're currently updating this, and I'll talk about that in a second. The next step was adding the web tool, which was done in the Bay Area, Outer Coast. And this is just an example from Pacifica. And what you'll see, and you've seen perhaps before on these slides, is this is obviously accessible online. On the left-hand side, you can choose what scenario you want. You can choose what storm you want. You can choose what infrastructure and other different data layers you want. You can export this information. This particular slide is just showing 1.25 meters of sea level rise in Pacifica without a storm. And then now this is with a very large storm, which shows sort of the value of having these storm impacts alongside just sea level rise. It changes the picture considerably in certain areas. Then we moved into San Francisco Bay. Along the outer coast, we went from about Bodega Head down to Half Moon Bay. And then with this version 2.1, we're in the entire shoreline of San Francisco Bay. The big addition here was trying to generate waves inside the bay. As I mentioned, you can get about 12-foot waves in the bay, so you need to be able to model that. You can't use a static bay with no waves at all. It can change the picture considerably in some areas. Also brought in river discharge from the Delta and other tributaries, and had to deal with this very extensive levee system. And the other critical factor in the bay is subsidence, vertical land motion. Most of the bay is subsiding about 1 to 2 millimeters per year, which is basically similar to the rate of sea level rise. So it can be, in some areas, as much as 2 centimeters per year, 10 times the global rate. So if you're not looking at how the land is moving, you could be missing a huge component of vulnerability. And the other big addition here was adding uncertainty to the mix, really trying to honestly assess the uncertainty of the model itself, the digital elevation data, vertical land motion, and also tidal wetland accretion rates. So here's an example from the airport, looking out just at 25 centimeters of sea level rise and an annual storm. So really just talking about several decades from now. This is the bullseye of the model. This is what the model says is the most likely answer. However, if you add all the different uncertainty that's possible in that projection, this is the potential outcome. So when you're looking at a high-end value infrastructure like this is what planners should probably be looking at. Not necessarily just the bullseye, but the full range, as Gary has mentioned. Lastly, now we're just gone back to Southern California. This is coming out next year. Very similar approach, scaling from global to local. The big addition here is the addition of coastal change to the picture. Before, we use a static coastline. We know the coastline evolves through time. The models are, I think, getting to the point where you can do this with some measure of certainty. So now we have an evolving coastline, and then we add storms to the mix. And sea level rise. Another really big missing ingredient, and something that we've been getting lots of feedback from policymakers, is what does this really mean in dollars and cents and people? So who cares? So what if this gets wet? You know, what is the actual impact to society? So we partner with Nate Wood at USGS, and we're actually going to have a webinar in a few weeks to roll out some of this data and try and get feedback about how to present it and how to make it effective for those various stakeholders. It's being done for San Francisco Bay now. It will be done for all of Southern California and everywhere else that Cosmos goes. So questions about how will land cover change, you know, ag, demographics, how many businesses are affected, how many people are affected, and what are the bottom line dollar amounts this type of each scenario will actually cause. So this is something I think speaks more to people at a higher level in you know, Congress, for example, that if you tell them you have, you know, X thousand acres inundated, they may not care. If you save $50 billion, then they may be able to get their checkbooks out and actually support some of the mitigation that needs to be done in a lot of these areas. So where are we headed? Future work. We're currently extending Cosmos in the Bay Area up to Point Arena on the outer coast with an emphasis on the Russian River mouth. I mentioned Southern California is being done now again with this more dynamic approach in terms of the coastline evolution and all the different scenarios, the 40 scenarios that we typically do. This is going to be completed in summer 2016 with the initial extreme scenarios coming out later next month. This was largely supported by the State Coastal Conservancy. Then we plan to move to Central California to be completed in 2017, and then the rest of the state tentatively by 2018. So we'll have full coverage of this dynamic approach, socioeconomic impacts that can be hopefully drilled right into for the use of local stakeholders for their climate impact mitigation needs. On a slightly tangential topic, we're also working with the National Weather Service to develop an operational Bay flooding model, which integrates both watershed-based flooding and ocean-based flooding. That's being piloted now and be available down the line about 5 years or so. So if you need more info, my email is there, website on Cosmos, and then also the Arcosta Future tool if you want to play with some of these scenarios and check them out. And we always welcome feedback not only on the accuracy, as you know it to be on the ground, which is really important. So it's really hard to validate a lot of these model results. Flooding is very rarely captured quantitatively. But also feedback on the kinds of products that are actually useful to you in your work is always welcome. So thank you very much for your time.